Hi, I'm Bruce Bonebrake. Welcome to this installment of the AutoZone Do-It-Yourself video series. Chances are you've seen the check engine light come on while driving. Today we're going to explain why the light is so important and what it means when it comes on and how to diagnose the problem. Then we'll show you how to reset the light once the problem has been corrected. Today's vehicles have several types of indicator lights to warn the driver of problems. First are the typical warning lamps that have been used for decades to alert us of low oil pressure, engine temperature, and so on. Warning lights are usually red in color and report on only one specific component or condition. For instance, a brake light that comes on when we try to drive with the emergency brake set. The second type of indicator, known as a malfunction indicator light, and usually amber colored, lets us know when there's a problem within one of the systems monitored by the car's onboard diagnostic computer. The check engine light is one of these. It illuminates automatically whenever the computer detects possible trouble with the emission control system, fuel mixture, engine performance, electrical circuits, or drivetrain. The light coming on does not necessarily mean that you have a big, expensive problem. Sometimes it can be as simple as a gas cap that has not been tightened properly. This is a good time to point out that not all cars have an indicator that says check engine. Your particular vehicle may have a service engine light, or it may have just an engine icon. No matter what type is on your car, when the light comes on, the vehicle should be checked for a cause of the problem as soon as possible by connecting a code reader, such as this one, to the vehicle to display the diagnostic trouble code stored in the system. Pay special attention to a check engine light that flashes while driving. A flashing indicator is alerting the driver to discontinue driving the vehicle as soon as possible because of a significant ongoing misfire. This can cause other systems to fail and possibly lead to expensive engine repairs if not addressed. You may be wondering why your vehicle needs a computer system and what it does exactly. Beginning in the early 1970s, car manufacturers were required to lower vehicle emissions. One of the first emissions devices was a positive crankcase ventilation, or PCV valve. Prior to the use of the PCV valve, vapors from the crankcase were simply released into the air. The PCV valve captures the vapors and reburns them in the combustion process. One of the next emission devices was the catalytic converter. The catalytic converter basically acts as a furnace to break down the pollutants created within the combustion process. By the late 70s, one of the first onboard computer systems was installed on select Chrysler vehicles. Other vehicle manufacturers soon followed. By the early 80s, the use of onboard computers to control the ignition spark timing and fuel mixture was becoming common. As emission laws got tougher throughout the 80s and early 90s, many different onboard computer systems were introduced by vehicle manufacturers. Unfortunately, most of these systems were manufacturer specific and in some cases vehicle specific. The complexity soon became expensive for the automotive repair industry. In the early 1990s, the EPA mandated that any vehicle sold within the United States must comply to a new standard called OBD2. It stands for Onboard Diagnostic System 2. All vehicles made during or after the model year 1996 have to comply to the OBD2 standards. An engine management system such as OBD2 can be divided into three main parts: the inputs, or sensors, the processing unit, or main computer, and the outputs, which are primarily fuel injectors, ignition coils, and transmission shift solenoids. The input sensors monitor a wide variety of conditions that could affect engine operation. The sensors feed this information via voltages and resistances to the main computer. The main computer is programmed to analyze all of these inputs simultaneously and make determinations on how to alter the fuel ratio and ignition timing of the engine, as well as when to shift the transmission to another gear. Let's talk about the critical conditions that input sensors need to monitor for proper engine operation. The first is throttle angle. Obviously, the computer needs to know how far the accelerator is being depressed by the driver. This will be a large determining factor in how much fuel the computer feeds the engine through the fuel injectors. The throttle positioning sensor is the sensor that monitors this. This sensor mounts on the side of the throttle plate on the engine. The next input is engine temperature. A cold engine needs more fuel to run than a warm engine does. Therefore, the system needs a way to monitor engine temperature. The coolant temperature sensor performs this job. It threads into the coolant jacket of the engine and constantly monitors engine temperature. The next input is air temperature. The air that is being taken into the engine can obviously vary greatly from winter to summer and region to region. Colder air needs more fuel to burn efficiently than does warmer air. So an air intake temperature sensor is used to monitor the temperature of incoming air. This sensor will be located somewhere in the air intake ducting or intake manifold. In addition to the temperature of the air entering the engine, the computer also needs to know how much air is getting to the engine. To operate efficiently, an engine must have the correct air-fuel ratio. This is typically 14 parts air to 1 part fuel. The way the engine management system knows the amount of air entering the engine is through what is called the mass airflow sensor. The sensor reports the amount of air entering the engine, and the computer will adjust the amount of fuel accordingly. Two more critical inputs are the position of the crankshaft and camshaft and their rotation. The computer needs to know the position of each so it can determine exactly when to fire the coil and fuel injector for each cylinder. There are trigger wheels attached to both the camshaft and crankshaft, and the sensors continuously read these trigger wheels to determine the exact location of the shafts in their rotation. Finally, there is a sensor that tells the computer how efficiently the engine is operating. Ideally, the system will deliver just the right amount of fuel and air to the engine and will burn all of the fuel and air completely. No fuel will be wasted. By having a sensor in the exhaust pipe, the computer can monitor if the engine is burning all the fuel-air mixture completely. The oxygen sensor performs this function and tells the computer if there's too much fuel or air in the mixture. The computer can adjust the amount of fuel up or down to correct. Now let's talk about the outputs of the system. First are the fuel injectors. The computer controls the injectors by opening and closing them hundreds of times per minute. The amount of time the injector is open is called the pulse width. The computer increases the amount of fuel entering the engine by extending the pulse width, meaning it holds the fuel injector open for a slightly longer period of time. It lowers the amount of fuel by decreasing the pulse width. Next are the ignition coils. The computer fires the ignition coil for each cylinder with precise timing. As engine operating conditions vary, the coil might need to be fired slightly sooner or later. In the old days, advancing the ignition timing was done via mechanical or vacuum controls. You probably heard of the vacuum advance system used on older cars. But today this timing adjustment is performed electronically by the computer. It will fire the coil sooner based on certain operating conditions such as high RPM. Many vehicles use a knock sensor as an input to determine if the timing is being advanced too far by the computer. This knock sensor picks up the vibrations from the engine that many of us would call pinging. If it senses excessive pinging, it tells the computer to adjust the ignition timing accordingly. This adjustment is critical to operate the vehicle at maximum efficiency. Now that we understand the components of the OBD2 system, let's move on and talk about how to communicate with the system and how to diagnose problems within the system. The system uses a standard connector so that diagnostic information can be obtained from any vehicle using the same diagnostic tool. This tool goes by several names, but most often you'll hear it referred to as a code scanner. This is the tool that you use to obtain the trouble codes from your system. When your check engine light comes on, the computer stores a trouble code in its memory. These trouble codes are read by the scanner, and that is how you begin the process of identifying the source of your check engine light problem. You can also take the car to AutoZone where they can help you determine the trouble code. The vehicle we're working on today is a 2001 Isuzu Rodeo. The check engine light came on, so we know it has at least one problem. To get a better idea of what's going on, the first thing I'll do is connect the code reader to the computer's data connector and retrieve the stored trouble codes in the computer memory.